E naught equals mc squared. This is probably the most famous physics equation that is known. It's more commonly said E equals mc squared, but E naught is what we refer to as the rest mass energy. And what this formula is telling us is that mass is just a form of energy, a very special form of energy. And it turns out to create mass requires quite a bit of energy because of this term right here, c squared. Remember that c is 3 times 10 to the 8th meters per second. And so squaring that gives you 9 times 10 to the 16th. So it takes a fair amount of energy to create any amount of mass, even a small amount. That's important because in the processes of fusion and fission, a tiny amount of matter is turned into electromagnetic radiation. We would say it's turned into energy. Of course, matter is just a form of energy, but you're taking that a little bit of matter and you're transforming it into a different form of energy. And fusion is what's going on inside the sun. So it is this process here, this formula helps us to understand where the sun is getting its energy and why it's able to get so bright and hot. And it's because fusion's going on and matter is being transformed into a different form of energy. Now, Einstein, of course, came up with this formula. He also came up with a different formula for kinetic energy. He came up with this formula: kinetic energy equals gamma minus 1 times the rest energy. Now this formula looks nothing like our traditional formula for kinetic energy. We have, of course, used this formula very many times. And these look nothing alike. Unlike, say, when you want to talk about momentum. The relativistic formula for momentum is gamma mv and the classical form is mv. It's easy to see how we get from the relativistic form into the classical form. But from here to here, they look drastically different. But in fact, this does turn into the classical form. And I want to show you how that happens. So first, we have to talk about the binomial theorem. There's an approximation using what's known as the binomial theorem, where if you have an equation, or I should say an expression like this, oops, I'm writing this wrong, 1 plus x raised to the n power, this is approximately equal to 1 plus nx if x is much less than 1. Now remember that gamma is really equal to the square 1 minus v squared. Here we go. C squared, 1 over the square root of that. And that can be rewritten as 1 minus v squared over c squared to the negative 1/2. Okay, so looking at this expression, this is in this form. So if we're talking about low speeds, so if this part here, if we're talking very small speeds, so if v is much less than c, then gamma is going to be approximately equal to, so I'm going to be putting it into this form here. I'm going to take this and put it in this form. So I'm going to have 1. Now my n is negative 1/2, so plus negative 1/2, and then my x is negative v squared over c squared. And so this gives me 1 plus v squared over 2c squared. So if I take this expression and I plug it into here, what I get is that kinetic energy equals 1 plus v squared over 2c squared minus 1. The ones cancel, and I'm left with v squared over 2c squared, and E naught is mc c squared. C squareds cancel, and what am I left with? Because these cancel, I'm left with mv squared over 2, or in other words, 1/2 mv squared. So what I've shown here is that for low speeds, so v much less than c, so non-relativistic speeds, this term that Einstein came up with reduces down to the classical form. Now, this expression here obviously has its uses. When you're talking about relativistic speeds, it does anyway. One thing it tells us is that the kinetic energy, if you rearrange it, the kinetic energy as compared to the rest energy is just equal to gamma minus 1. Now, gamma goes from 1 to infinity. So at 1, that's when an object isn't moving. This is 0, so that's just telling us the kinetic energy is 0. But as an object moves faster, gamma is going to get larger and larger. Eventually, gamma will get to 2. 2 minus 1, of course, is 1, and that's telling us the kinetic energy equals the rest energy. And then beyond that, the kinetic energy is going to be greater than the rest energy. So, it's possible to go through and figure out, hey, how fast does an object have to go in order for the kinetic energy to be greater than the rest energy? I'll leave it for you to work out, but I'll just tell you the answer. It turns out that for that to happen, kinetic energy equals the rest energy when, and of course that's when gamma equals 2, when gamma equals 2, which also means that the speed is equal to the square root of 3 over 2c, which is approximately equal to 0.866 c. So really fast. I mean, we're talking extremely high speeds. It takes extremely high speeds for the kinetic energy to be the same as the rest energy. And I'm pointing this out because this is another way to help illustrate just how big rest energy is. Matter itself is just a huge amount of energy. And, again, we can see that by looking at this formula, but then this helps kind of bring it into light because you have to go ridiculously fast before your kinetic energy will be the same as your rest energy.